Hello, everyone. My name is Aicardi. I'm a recent graduate from the BL Lab, and today I want to talk to you about a recent project we submitted to biochemistry effects of Aicardi Goutières syndrome causing mutation on catalysis of adenosine deaminase by ADAR1. ADAR enzymes are double-stranded RNA binding enzymes that specifically catalyze the deamination of an adenosine to a functional mimic of guanosine. This is catalyzed by two specific active isoforms, ADAR2 and ADAR1. Within the ADAR1 family, we have P110, which is nuclear localized, and P150, which is localized in the cytoplasm. Turns out the P150 isoform of ADAR1, its A to I editing event is pretty critical in regulating cytoplasmic immunity, where the structural change caused by A to I deamination prevents recognition of these double-stranded RNA structures by these immune recognition receptors that then prevent translation shutdown, RNA degradation, or immune infiltration. This is a mechanism by which self-double-stranded RNA are protected from these immune regulation pathways. Therefore, any loss of function mutation within the P150 gene of ADAR1 is associated with immune disorders, including Aicardi syndrome. Within the ADAR1 gene, there's 8 mutations found. 7 of them actually map within the deaminase domain of the protein, and 1 maps to the zDNA or zRNA binding domain of the protein. And while there have been cellular studies done with overexpressing these plasmid containing these AGS mutation in HEC290 cells, these studies don't reveal how the ADAR1 catalysis is affected. So we wanted to provide comprehensive biochemical studies in understanding how these mutations impact rate of catalysis, RNA binding, protein-protein interactions, and so on. And these studies have been limited in the field due to difficult purification of the ADAR1 protein in its full-length and truncated variants. And we were able to introduce, through developed purification methods, these mutations in ADAR1 P110 and truncated variants ADAR1 R3D containing just one RNA binding domain, and finally just the deaminase domain of the protein. By systematically studying these mutations within these full-length and truncated variants, we are able to decipher which mutations were most detrimental to RNA binding and catalysis. Collectively, what we found was the mutation that are most adjacent to that flipped out adenosine is critical for activity. So these mutations include G1007R and R892H. G1007R disrupts catalysis because it is within the flipping loop of the protein. We know ADARs act by base flipping mechanism. And G1007R disrupts this base flipping mechanism, is detrimental to catalysis in all of the full-length and truncated variants. It also affects binding of AAZN-bearing RNA, so it makes a very poor protein-RNA complex. It also inhibits wild-type activity. And finally, it also disrupts ADAR1 dimerization. And it is important to note that this mutation is heterozygous only. R892H was the second detrimental mutation. It was detrimental to catalysis across various constructs. It was also, it had inhibitory effect in wild-type activity as well. This mutation is also mostly found as a heterozygous mutation. Finally, mutations that are distal to the active site were less detrimental to activity or had context-dependent effects. That includes K99N and Y112F mutation, which is most distal, had the least impact on catalysis. If you want to learn more about this project, please visit my poster. Thank you for your attention.